Hi everyone. Now we are going to discuss on the various methods which is employed in order to turn on the thyristor. Basically, there are five methods in order to turn on the thyristor. That is, which is mentioned over here: the forward voltage triggering, gate triggering, dV by dt triggering, temperature triggering, and light triggering. So we said that an SCR is a semi-controlled device. An SCR is a semi-controlled device. That means you have your control over the turn-on process. So these are the methodologies which we are implementing in order to turn on a particular thyristor. So first we will be seeing about the forward voltage triggering. The forward voltage triggering we have already discussed when we are discussing about the IV characteristics of the device. So it is again repeating it. Again, it is very simple. As you can see here, you have your thyristor block schematic is mentioned over here. You can see over here there are three junctions are there: J1, J2, and J3. In the case of a forward voltage triggering, the gate voltage is 0. That means you are not applying any gate supply. And what you're trying to do is that you're trying to give a positive voltage across the anode and a negative voltage across cathode. Now, and this condition, this J1 and J3 becomes forward biased. J1 and J3 becomes forward biased, and junction J2 will be reverse biased. And that means a small depletion layer will be formed across the junction J2. Now what happens is that we are trying to increase the forward voltage which is applied across the anode and cathode. When we are trying to increase the voltage, what happens is that this depletion layer starts reducing its width. The width of the layer will be decreasing, the increase in the anode to cathode voltage. So at the end, more and more voltage which is given to the system, what happens is that at the end it will result in the avalanche breakdown, and that means at the end the junction J2 will be vanishing away. So that means the device will goes into conduction mode. So this can also be seen from the IV characteristics which you have already plotted. We have here a positive voltage VA and the anode current IA. So it will go like this. It reaches to a point over here, and it will reach a particular voltage which is known as the VBO. So this voltage is nothing but VBO. At this juncture, what happens is that the device goes into conduction. So this is how we can explain the forward voltage triggering. And generally, the forward breakover voltage VBO is normally taken as the final voltage rating of the particular device. So after the avalanche breakdown of the junction J2, the junction J2 loses the reverse blocking capability. So even if you reduce the voltage VBO, which is applied across the anode and cathode, below the breakover voltage, the device will remain in the conduction state, and the device can be switched off only by reducing the current below the current called as holding current. So that is where we are explaining about the forward voltage triggering. But this kind of among these kind of triggering, gate triggering is the most prominently used, and forward voltage triggering is not advisable to have in an thyristor system. Now next we will be seeing about the gate triggering circuit. Now we are going to discuss on the gate triggering method of turning on the thyristor. For that purpose, you consider a thyristor which is having a rated breakover voltage of 800 volt, and you are connecting it across a working voltage of 400 volt. And since this working voltage is much lesser than the rated breakover voltage, the device will not go into conduction mode by forward voltage triggering. So you can say that your anode is made positive, cathode is made negative, and that means junction J1 and J3 becomes forward biased, and junction J2 becomes reverse biased. Because of this reverse bias junction, a depletion layer is formed across the junction J2. Now, in order to make this device into the conduction mode, you have to give a gate supply. So the gate is being supplied by giving a positive gate current across the anode and cathode. Now that will result in the flow of current Ig. There is a difference in the doping levels on the different layers of this thyristor. So N2 is heavily doped and N1 is lightly doped. Now, when you are trying to give a positive gate current across the gate and cathode junction, that will result in the electrons which is concentrated more in the N2 layer to flow across the junction J3 to reach P2. So these electrons which are there in the P2 will be again swept across the junction J2 by crossing the depletion layer. Therefore, that will reduce the positive space charge. That will reduce the positive space charge on the N1 side of the depletion layer. So this width of the depletion layer will go on reducing, and at the end the junction J2 get breakdown and the depletion layer get vanishes and the system goes into the conduction level. Now that is for a particular current of Ig. That means if you are increasing the value of Ig, then the device will get turned on at a much lower forward voltage applied across the anode and cathode. That again we can see from the IV characteristics of the device. So the rated graph, if I am plotting it over here, it is 800 volt, which the device is not going to start because you are giving only a supply voltage of 400 volt. So at this 400 volt you are giving a value of current Ig. Let it be Ig1. So the device will go into the conduction mode at 400 volt. Now just imagine that I am increasing from the Ig1 to Ig2 greater than Ig1, then the device will get turned on at a much lower forward voltage. So let it be V2. So this is for Ig2, and this one I will take it as V1, and this is Ig1. So in effect I can write that if Ig2 is increased much above Ig1, then the device will get turned on at a much lower voltage when compared to that voltage with respect to the Ig1. So once the device goes into the conduction mode, the depletion layer is getting vanished, and now the device will remain in the turn-on mode. And the gate circuit we can remove it. This gate circuit we can remove once the device goes into the conduction mode. And it will not affect the conduction, and that is where we need to again think back about what we have studied in an earlier lecture about the latching current. So if this anode current which is flowing across the device is greater than the latching current, then obviously you can remove the gate circuit from the system and the thyristor will remain in the on state. Therefore, latching current can be defined as the minimum value of the anode current which it must attain during the turn-on process to maintain the conduction when the gate signal is being removed. That means if the anode current is greater than the latching current, then we can remove the gate signal. The device will remain in the on state. We can plot the variation of gate current for different values of breakover voltage like this. This is for Ig, and this is your anode voltage Va, and we can plot it over here. This is for Ig1, this is Ig2, and this is Ig3. So from here we can see that Ig3 is greater than Ig2 is greater than Ig1. So if the gate current is smaller, then the amount of forward voltage which is required for making the thyristor to turn off is lesser. So the point will be coming over here. If Ig2 is lesser than Ig3, then more amount of forward breakover voltage is being required, and that is, we can plot it over here. And if still your gate current is still reduced, then you need more amount of voltage across the device to make it into the turn-on device. Therefore, we can plot a graph like this. So these are the different values of forward voltages. You can say that these are the forward voltages which is being required in order to get the device into the turn-on condition. Now we are moving on to the third method of turning on the thyristor, that is dV by dt triggering. So we will be applying a positive voltage across the anode and cathode. Junction J1 and J3 becomes forward biased and junction J2 becomes reverse biased. The reverse biased junction J2 will be acting like a capacitance because of the charges existing across the junction J2. Now if you are applying a sudden change in voltage to the system, then it can make the system to be in the turn-on mode. So that can be explained with the help of the equation. Like if C is the capacitance, across the junctions, I denote it as Cj, and V is the voltage applied across the device, and let Q is the charge. Then we can write I is equal to dq by dt, but q is nothing but c into v, so it is d by dt of cj into v. This again we can write it as cj into dv by dt plus v into dcj divided by dt. Now this term can be neglected because the capacitance across the junction is almost constant. So this term will get vanishes away. So at the end I can write it as I is equal to Cj into dV by dt. Now if the rate of change of this voltage across the device is large, then the device will get turned on even though the voltage across the device is very small. So that is by the dV by dt method of triggering on the thyristor. Now we will be seeing the temperature triggering method of turning on the thyristor. It is also known as the thermal triggering. So when you are forward biasing the thyristor, junction J2 is reverse biased, that is a depletion layer is formed across the junction J2, and the entire voltage will be applied across the junction J2 because junction J1 and J3 are already in the forward biased condition. So this voltage across J2 will result in the leakage current and would raise the temperature across the junction J2, and this temperature further leads to more amount of leakage current. So with the increase in the temperature, the width of the depletion layer decreases, and as a result of that, more amount of charge carriers will be flowing across the junction. So therefore, more the junction temperature, then more amount of carriers will be trying to flow across the depletion layer, which will reduce the width of the depletion layer, and it goes as the cumulative action, and at the end the reverse bias junction vanishes away and the device goes into the conduction mode. That is about the temperature triggering. It is also known as thermal triggering method of turning on the thyristor. Next is the light triggering or radiation triggering, and this is being made possible by imparting radiation onto the thyristor device. You can say that a small recess is made in the P2 layer on which you are impinging your light. A light radiation is given onto this particular recess. So whenever such a light is being impinged on that particular layer, free charge carriers are generated, just like when a signal is applied by a gate signal. So in the same way, action whatever it is happening in the case of a gate triggered thyristor will be happening once the light is impinging on the P2 layer and the device goes into the conduction mode. So these are the mainly 5 methods of turn-on methods in the case of a thyristor. So in that we have seen forward voltage triggering, gate triggering, dV by dt triggering, temperature triggering, and light triggering. In that, most commonly used and most simplest method is nothing but your gate triggering method.